This is the famous General Radio Company GR-1236 IF amplifier, much sought after by EME moon bouncers. It is a 30 megahertz IF amplifier with very high gain, nearly 100 dB of gain, and a noise figure of only 2 dB. And it has a calibrated step attenuator and a meter scale, which allows you to look at the signal level or noise level to 1/100th of a decibel. Yes, 1/100th, 0.01 dB. You'll notice the 1 dB scale here. Now this instrument came from South Korea, and that is why it is in pristine condition. It uses a combination of novistors, regular vacuum tubes, silicon, and germanium transistors. Let me move this cabinet out of the way. You can see the voltage regulator transistors. There are many power supplies in here. 66 volts for the novistors, regulated. This is the regulator tube here for that, 6DR7 dual triode. And there's 12.6 volts regulated for the filaments of the novistors and the transistors. And then there's a separate variable power supply for an optional mixer. So if you put a mixer ahead of this, you can down convert from up to 9 gigahertz using a crystal mixer to the 30 megahertz IF. And then there is an output from the IF, in addition to this meter. If you wish to connect it to a narrowband crystal filter, CW filter, add a BFO, you just have to connect it here to these terminals down here. This one is a IF output. This is the IF input, the famous GR connector. I'm going to need an N adapter for this. So here's a brief tour of it. This is a novistor from RCA, a sample that I have. It's as small as a transistor, but it's a vacuum tube. It has a filament, a cathode, a grid, and a plate. So there are 3 novistors used here in a cascode circuit, 1, 2, 3. And this provides a gain of 28 dB from the input connector, where you have the 2 dB noise figure. There's a tuned circuit, another tuned circuit, another tuned circuit, and you can switch resistances, shunt resistance across that. The 3 dB bandwidths are selectable between 4 megahertz and 500 kilohertz. And then there's a step attenuator, which is in 10 dB steps. Now, why do you need such a high bandwidth? Why do EMEers want this so badly? Very simple. If you use a narrowband radio like an ANAN, and even if you put it in the widest IF position, 10 kilohertz, or if you're using an ICOM FT series radio and you're set up the IF bandwidth 3, 4, 5, 6 kilohertz, 8 kilohertz, there's no moon noise there. The bandwidth is too narrow. You've got to have megahertz, or at least hundreds of kilohertz of bandwidth. And it's got to be flat, and you've got to measure it. And that's how you get the moon noise to actually register on the meter. So after this step attenuator, which is calibrated in 10 dB steps, we come to a solid state IF amplifier, again with tuned circuits. And this provides 70 dB of gain. So the 70 plus the 28 is 98 or almost 100 dB of gain from the IF input connector to the IF output connector. And of course, these detectors drive the meter circuits. They also drive an optional AGC circuit, which is not normally used for moon bouncing. That is just simply used if you want to use this as a null detector, and you need to keep the IF amplifier in a linear range while you're getting the null. So that's the only purpose for that. And then there's the meter detector and the meter driver. So normally the IF signal from this detector here, this diode, goes into the meter and to ground on the setting and position number 4. But on the 1 dB scale, a differential amplifier is added, and this provides extremely high gain, and it's balanced Everything is temperature compensated. Even the IF amplifiers, there are diodes feeding back to the emitter to change the current through this plate circuit. There's DC voltage on there, and it's all temperature compensated. There's no drift. Everything is regulated. The voltages are regulated. The temperature is regulated. You have constant gain. And you can see here the scale. The dB scale, 31 is 0 and 100 is 10. That's your 10 dB. And then between 9 and 10, if the needle is in there and you expand to the expanded scale, that 9 becomes 0 and that 10 becomes 1. So between 9 and 10, if you go on the expanded scale, you can read it out here. And as you can see, you have a resolution on these minor ticks in between. You can actually measure 0.01, a hundredth of a dB. Yes, 1/100th of a dB change in noise. This is incredible. It's all averaged, and that's what a analog mechanical meter does. It averages. So you would see a 0.01 dB increase in noise. This is a very specialized piece of equipment and extremely rare. It cost me $1,000 American to get this, and he shipped it real fast. I mean, it was 2 days on the plane, and it's here from South Korea. But it's in mint condition. Absolutely mint. Isn't that gorgeous? And this was made in 1968 during the Apollo moon program times. And many of these were used to measure noise for the moon communications trials and to set the baseline for the dish antennas. This instrument can be used for doing radiation field checking, antenna pattern measurements, because it's so sensitive. It's just wonderful. So this is the most sought after piece of equipment for EME moon bouncing. And you know what's really interesting? If you connect a transverter with a 30 megahertz output here, and your antenna, and you connect the IF output to a small filter with 500 hertz bandwidth at 30 megahertz, or you down convert it again to an IF frequency and add a BFO, you have a full moon bounce receiver with gain controls and everything. This is a standalone moon bounce receiver. This is why it's so sought after, but it is especially useful for noise measurements because of the resolution in the noise dB scale. It's incredible. So I'm going to power this up slowly and form the capacitors as a first step and make sure all the DC voltages are correct and check the calibration. I've got a dB meter here, which I can use because I'm going to be looking at the output, audio output, and I can easily check. And I've got my signal generator down here, and I've got my power meter, so I know exactly how many dBm I'm feeding into this, and I will be able to do a full calibration on the unit, and we'll see. I'm so thrilled with this. This is going right back to the Apollo 11 era, 1968, 1969, when General Radio was king and HP was really just gaining a foothold at that time. General Radio was the test equipment company at the time. Look how well constructed it all is. It's absolutely gorgeous. Everything's hand wired. You've got military PEC potentiometers. Everything is modularized. It's on hinges, so the board flips up. You can get to every single part of the circuitry. There's even a demodulator output because there are two detectors, one for the meter and for the AGC amplifier, and another one which has a wideband video output. It has a 1 megahertz bandwidth. So you can even get video signals out of here of some type. That's what it was designed for. It's just incredible. The General Radio 1236.